In this section, we're going to consider rounding and errors gotten by rounding and margins of error. Let me start with this example meant to remind you of how to do this kind of stuff. We're told to round each of the following numbers to the nearest tenth and the nearest 10. So let me start with part A, and we'll start with tenths. Well, if you'll recall, you have to remind yourself where on the numbers is the tenths position, and it's right there. It's the first number after the decimal point, so that's our tenths position. Now hopefully you'll remember that what determines whether you round up or down is the digit that comes after it. So let me erase this arrow here. So there's my digit. When I round up or down, that digit will change either to a 4 or it will stay the same. The number behind it, this one right here, this 1, if that is less than 5, then you're told to round down. If it's greater than or equal to 5, you round up. Since this 1 is less than 5, I'm going to round down to 475.3. Now for the nearest 10, this time we look at the nearest 10. Well, the tens spot is right here. Notice that across the decimal point it's not completely symmetric. If you look, there's a 1 spot on the left of the decimal, but on the right of the decimal there's no 1th position. It starts in the tenths, so it's not completely balanced here, so be careful. So my 10 spot is that 7 there. It's either going to turn to an 8 or it's going to stay the same. This 5 that comes after it tells me to round up. So that means I'm going to have 4, 8, and then 0. Now when you round to the nearest 10, you can leave your answer like this because I've got it in a 10. So technically speaking, that's the best way to answer that because it is the number, it's the 10 that is closest to the number that we had. Same situation for B. Let me start with, well, let me write it down, 973.823. So I'll start first with the tenths. Here's my tenths location. And the 2 after it tells me to round down. So I have 973.8. And notice you can stop the decimal at the tenths because they were asking to find the nearest tenth. So technically speaking, your answer should be in terms of tenths. So that there is going to be the nearest tenth. And then over here, 973.823. Now I want the nearest 10. So once again, there's my spot for the tens. 3 tells me to round down, and I end up with 970. Part C, these are the tens. Part C, we have 625.3. Now the nearest tenth, let me write this. Now it doesn't look like there's a digit after there, but technically there's a 0. So we're going to round down and get 625.3. That's to the nearest tenth. Now for the nearest 10, I look at this 2. After it, I see the digit is a 5. So I can round this one up. So this would be 630. And the last one, there's nothing special about the negative that you have to even pay attention to. We start negative 93.634. That 6 is in the tenths spot. I round down, and I get negative 93.6. On the other hand, the tens spot is here. That means I round it down to negative 90. For this problem, recall the following. The absolute error equals measured minus reference. So in this first problem here, we have the true height is going to be the reference one because that's the one we're going to measure against. So for this problem then, our absolute error will take the measured diversion, 67.7 inches, and we will subtract the true height, which is 68.0 inches, and we end up with negative 2.3 inches. Now for the relative error, or the percentage error, we take the measured value minus the reference, and divide by the reference. And then finally, we turn that into a percentage by multiplying by 100%. So look at here on top of the fraction, the measured value minus reference is nothing more than the absolute error. So let's throw our numbers in here. I'm going to have the measured value is 67.7 inches minus 68 inches, 68.0 inches. Divided by 68.0 inches times 100%. Let's grab the calculator and calculate this number. 67.7 minus 68.0, that gives me the negative. I made a mistake on the first one. Let me come back for a second before I finish here. I made a mistake there. That is not 2.3. I don't know what I was thinking of. This is negative 0.3 inches. All right, let me finish then with this. So I got my top part. Now divide by 68 inches, or 68.0 if you really care, and then multiply by 100. And if I go to 2 decimal places, it looks like negative 0.44%. All right, in this one, they give us the reference. That's the true price. That's that guy right there. And then this is the measured value, if you would like to call it that. So our absolute value, our absolute error, is measured minus the reference. And our measured was 19.31, that's dollars, minus 18.65. And that looks like 66 cents. Then the relative error, that's measured minus the reference divided by that same reference times 100%. Let me get my numbers in. My measured was the 1931. The reference was 18.65. And I'm going to divide by that same 18.65 and multiply it by 100%. So take my 19.31 minus 18.65, hit enter so you get it equal. So there's my first answer. I'm glad I got that right. Now I'm going to divide by 18.65. And now I'm going to multiply by 100%. And I'll round to 2 decimal places here. It looks like 3.54%. Here we are measuring a flower bed by walking around it and guessing our footsteps. So we have 10 3-foot paces. So that's a total of 30 feet. Of course, there's our measured value right there. So let's go ahead and do our absolute error. That'll be measured minus the reference. So our measured was 30, well, our measured is the 30 feet. And we're subtracting 32.1 feet. That's the reference. We're going to take the tape measure as the accurate one. And I end up with negative 2.1 feet. Then our relative error, that's measured minus our reference divided by reference again times 100%. So we've got our 30 feet minus 32.1 feet divided by 32.1 feet times 100%. 30 minus 32.1, enter. Divide 32.1 equals, and now multiply by 100. And it looks like negative 6.54%. So there's my absolute, there's my relative. Here we have the actual body temperature of an animal that's given. So this here would be our reference value here, since we know that to be true. And this is our measured value here. Once again, absolute error. That's going to equal the measured minus the reference. The measured is 24.48 degrees Fahrenheit minus 24.3 degrees Fahrenheit. That ends up being 0.18 degrees Fahrenheit. And then a relative error, that's measured minus ref divided by ref times 100%. So I'll get my 24.48 degrees Fahrenheit minus 24.3 degrees Fahrenheit divide by 24.3 degrees Fahrenheit, and then multiply by 100%. 24.48 minus 24.3, enter. Divide by 24.3, enter. And then multiply by 100. Enter. So mine is 0.74%. This example may sound very, very strange, but what we're trying to do is get you to understand the precision that is expected of you when you do something. Whenever you do any kind of work, scientific work, the data that you get may come in various precision levels. Look at this, for example. 0.8 of a pound is to a precision of 1/10, or 8, it's 8/10 of a pound. But here, they have no decimal. It's just a whole number. So they rounded to the nearest tenth for the pounds there, but here it's rounded to the nearest 1. So what was your weight before you ran? Well, it was 138 pounds plus the 0.8. So I have to put a 0.0 to add them. Now, what you do when you report your answers is you report it in terms of the data that had the least amount of precision. I have two options for my answer here. I could do 138.8 or I could do 139. 139 is the correct answer here because this number 0.8 is rounded to the nearest tenth. That is of a higher level of precision than something that's rounded to the nearest whole number. So since my lowest level of precision is a whole number, I'm going to take my final answer and round it to a whole number. So that's actually the correct thing to rewriting there, and you should probably put the LB at the end of it. So that's the rule. When you're doing some sort of work and you have a bunch of numbers that you're dealing with, when you go to report your findings, you use the precision level of your least accurate number. Another example with mixed precision here. We have the first thing is in whole numbers. So it's rounded to the nearest unit, I suppose you could say. And here is 2 decimal places of accuracy. So the final answer I'm going to report is going to be a whole number. So to actually do the computation, they want us to do 107 miles divided by 0.66 hour. 107 divided by 0.66. So I get 162.12 if I go to 2 decimal places. Now, that's not going to be the answer that they want. Once again, this has 0 places of accuracy, well, 0 decimal places of accuracy, and this has 2. The least precise of the 2 of these is the whole number. So I'm going to round this to the nearest whole number, and that's going to be 162 miles per hour. In this example, we have weight given in pounds and ounces and weight given in ounces. Now, one thing that you don't want to ever do whenever you're working on a problem is have a mixture of units that you're dealing with. So I'm going to change, I think it's supposed to be a 7. I'm going to change 7 pounds 11 ounces to completely just ounces. So for that, I need to know that there are 16 ounces in a pound. So if I want to do 7 pounds, that's going to be 7 times 16 ounces. And that's 112 ounces. 7 pounds is 112 ounces. And then I'm going to add the 11 ounces. So take 112 ounces and add the 11 ounces to it. So I have 123 ounces there. Now, that's how much our baby weighs in whole ounces. To get the total weight, we'll take the 123 ounces and I'll add to it the 14.8 ounces. I'll put a 0.0 to make that compatible. And it looks to me like I'm going to get an 8 here, 3, 7, 3, 1. Now, we need to round this the correct amount. So these ounces were given as whole ounces and these ounces were given in 0.10 increments. So for that, we're going to round to the nearest whole number and do 138 ounces. per capita cost is how much it is per person. So we're going to take the $2.6 million and divide it by the number of people. So we're going to have 2,600,000 divided by the number of people, 150,162. Let's call them PPL. 2,600,000 divided by 150,162. 17.31, let's say. That's per person. However, let's take a look at our data. I have this here is not, there's no decimal involved in that. It's a whole number. There's no decimal involved in this. It's also a whole number. So what I'll need to do then is convert my final answer to a whole number and just change this to $17 per person. In this last example, we're presented with two types of error situations here. Keep in mind the way this guy or this person is deciding to do the measuring of 15 lengths of wood. He's trying to get 15 of them exactly 4 feet if they can, but that's not always possible, of course. So the error here in part A, we see that each time he cuts a board, he could shave off plus or minus 1/3 of an inch. He could be 1/3 of an inch too short. He could be 1/3 of an inch too tall. So how far can it be for the 15th one? Well, if you look, let me draw a few things here. For part A, if you look at how off, let me call it this way, how off. So, and then we'll take a look at the board numbers. So board 1 can be 4 feet, but plus or minus 1/3 of an inch. So let's keep a low and high end on this. So the low end, now 4 feet is 48 inches. So I'm going to take 48 inches minus 1/3 of an inch. And that will give me 47 2/3 inches. And then for my high, I could have added, so I'd say 48 inches plus 1/3 of an inch. That equals 48 1/3 inches. Now look at board number 2. So my low is going to be 1/3 of an inch less than the one before that, because remember, I'm using board number 1 to get board number 2. And that is still subject to a plus or minus 1/3 of an inch error. So my low, I'll shave off another 1/3 of an inch. I should put the inches in here. It looks like 47 1/3 inch. And over here for the high, we take this number here and add 1/3 of an inch to it. So 48 1/3 plus 1/3, that'll be 48 2/3 inches. Keep going. This time I'm going to subtract another 1/3 of an inch from this. So my low will be 47 and my high will be 49. So I subtracted 1/3 from this last number. I added 1/3 to this last number. Well, hopefully you can see there's a pattern here. After 3 of them, the low is 1 inch lower and the high is 1 inch higher. So because it's the same amount for every single board, what you can do is this. For all 15 boards, I could take 15 times 1/3 of an inch and get 5 inches. So if I want a lower estimate for my boards, I can take the length of the board I want, 48 inches, and subtract off 5 inches to give me 43 inches, and that's the lowest possible length of this 15th board. We call it the 15th board. And then a high, we're going to have 48 inches plus 5 inches, and that's 53 inches. So there are my estimates for the lowest and longest possible board. Part B, let me recall it. Actually, let me come back here and grab part B. Now this time the error is given in terms of percentage. This is different because in the previous part A, you always cut off or added the same exact amount every time. But if the error is related to the length of the board, then as the board is shorter, the error is smaller. When the board is bigger, the error is bigger. So watch how, let me do board 1. What do? We take it was supposed to be 48 inches, and then I want to subtract 0.5% from it. So this is the calculation you'll have to do. I'm going to factor out 48 inches and convert that 0.5% to a decimal. Hopefully you can see that. When I factored the 48 from this first piece, it left behind a 1. When I factored the 48 from the second piece, it left behind 0.005. And you can have your calculator do this, especially if it lets you see what you type in. So I'm going to have 48, and then I can do a parenthesis. See this? It'll automatically assume it's multiplication, and then I go 1 minus 0.005, and I'll finish off the parenthesis and hit enter. So I get 47.76. That's board 1. This is on the low, that's the low end. For the high end, we're going to take our 48 inches, but we're going to add 0.5% to it. When you factor out the 48, here's what you get. And that's, of course, is in inches. Let's use the calculator. 48, start a parenthesis, 1 plus 0.005, end of the parenthesis, and hit enter, 48.24. Now, you're going to use these results to build on the next one, because what you're going to do is you're going to subtract 0.5% from this low estimate to get a new low estimate, and then add 0.5% to get a new upper estimate. So we move on to board 2. So what do? I do just like I did before, except this time I take 46.76 IN, what I ended up with before, and multiply by 1 minus 0.005. That's the low amount. Likewise, up here, if I want the upper amount, these are inches. Let me use the calculator. 47.76 parenthesis 1 minus 0.005 end of the parenthesis, and I get 47.5212. Notice it's a little bit less than it was before. Now you should round appropriately. Since this is actually 3 decimal places, the percentage is in 3 decimal places. So I would probably keep all of my accuracy to 3 decimal places. So I'm going to go 47.521 inches, 48.24 start the parenthesis, 1 plus 0.005, end the parenthesis, enter. I'll write 48.481. And those are the numbers I'll use for my next round. Do it again. I'm going to take my 47.521 times 1 minus 0.005 inches. And for my large, I'll get 48.481 times 1 plus 0.005, 47.521. Start my parenthesis, 1 minus 0.005. Finish the parentheses. And I'll do 3 decimal places, 47.283. And for the high estimate, we're going to have 48.481. Start a parenthesis, 1 plus 0.005, end the parenthesis, enter. And it looks like I'm going to get 48.723. And that should be inches as well. Now keep track what's going on here. Here so far, we have gained 0.723, almost 3/4 there, 0.723. But over here, we're 0.717 below 48. So they're not going to be equal. This low amount's going to not do as much as far as dropping the values so much as this one on the right raises the values. Now, you might notice that what we've done so far is when I started with the first board, I had 48 inches. So I took 48 and I multiplied it by 1 minus 0.005, and that was the first board. These are the low estimates. But then all I had to do to get the second one was this. Each time just multiplying by a new number. There's the third one. I just have to keep this going until I get to the 15th one. Well, that's no different than 48 times 1 minus 0.005 raised to the 15th power. Something my calculator is quite able to do. Let me show you how it works on mine. Maybe you can figure it out on yours. So we'll start with our 48. I'll start a parenthesis, 1 minus 0.005. Finish the parenthesis. Now, let me pull this out so I can see what I'm going to do. I got to raise x to the y, and I'm going to put a 15. That should work. I hit an enter, and I end up with 44.523. So those are my low estimates. Now for the high estimates, here we're going to do 48 times 1 plus 0.005 raised to the 15th. 48, start a parenthesis, 1 plus 0.005, and then let me raise it to the 15th power and hit enter and see what we got. 51.729. And then you'll be required to round these, I'm sure, to a certain degree of accuracy.